And next up is that's part B, right? Now, I wonder whether we have enough information to be able to multiply this by the mass flow and then have the answer in watts instead of energy per mass. We need to check that. We need one state fully defined to be able to do that with all the info. And we have these two fellas, but we don't have the volume. We don't have specific volume. No, not any mention, nor any mention to mass flow. So we can't. That's the best we can do. So really, we can't really go to the watts here. We're going to have to settle for energy per unit mass. All right. This is done. This is done. Thermal efficiency. Now for the easy part. We did all the hard work. Now thermal efficiency. Thermal efficiency is how much I was able to get out of my system divided by how much I had to put into my system. What I had to put in was the heat addition process, which we know 750 kilojoules per kilogram. What we got out, 392.4, also kilojoules per kilograms. So this tells me that my thermal efficiency of this guy here is 52.3%. Okay, so for every little bit of energy I put on the heat addition process, I'm getting about half of it out as useful work. And then last, probably the most weird or most different part of the problem is, what is the effective mean effective pressure? And we talked about how this was just work divided by volume. It's just an assumption that we can get the one single pressure for the whole cycle, which is not the case, and then what that would look like. And here we have the volume. Oh, so if we're going to calculate the volume, that means we can go back and convert this into watts. All right, we should do that. Okay, because this we know to be 392.4, which is great. But then the difference in volume we don't have, right? We don't have the difference in volume. To be able to grab this difference in volume, I'm going to need to use what is my volume? PV equals MRT. I have T, I have V, so my volume will just be mass RT divided by P. I don't have the mass, but I can divide everything by the mass, so I'm going to have specific volume equals RT over P, and that I can do. Right, that I can do. So if that's the case, then all I need to do is use the R for the ideal gas constant for air, 0.28, right? So that's 0.287 in kilojoules and what's the unit again? Kilojoules per kilogram Kelvin. Then multiply by T1. T1 was 300 from the start, Kelvin. And I'm dividing that by the pressure, which is 95 kilopascals. So what happens here is Kelvin and Kelvins go away. And then kilo and kilo goes away. And then joules and pascals, they can cancel so that we're left with meters cubed. So that's going to be meters cubed per kilogram. So that means my specific volume 1 is 0.906 meters cubed per kilogram. Whew. So that's one of the volumes, or a specific volume anyways. And then for the second one, I'm going to have to do the same thing, right? So V2, that will be RT2 P2. In this case, same value, obviously it's a constant. But then my temperature is different. My temperature on state 2 is 673. Actually, I can do the ratio between the volumes is 8, right? So I can just do 8. Yeah, it's 8. So we don't need to do the whole thing. if we don't want to. We can just do 8. But the other option is just keep going here, and then that will be this 0.1 divided by pressure, which is 1705. Okay, but there's a ratio. Remember, there's a ratio between V1 and V2. We actually knew that from the start too. We knew that V1 was 8 times V2, so therefore V2 will just be 0.9 divided by 8. 06 divided by 8, which gives me 0.33. Okay, so that's another option. Forgot about this. This is actually easier. So I'm going to grab this, place it here. I'm going to grab this. I'm going to place it here. We know that as we're going from state 1 to state 2, state 1 to state 2, this needs to be, so this needs to be like so. Same units, that's fine. Kilojoules per kilograms here, it's fine, so that we get rid of the kilograms. And then same thing happens, right? The joules and the meters cubed, so that's going to be left with pressure. It's going to be in kilopascals. That's going to be in kilopascals. So this turns out to be, what is my mean effective pressure? 495 kilopascals. Okay, we're integrating from 1 to 2. That's going to be energy. Oh, this is going to be negative if we're going from 1 to 2. No, this is not 1 for 2. This is... Oh, this doesn't matter, right? Because the volumes are the same. So it doesn't matter if whether it's negative or not. Okay, beautiful. That makes sense. All right, this is definitely a long question. So, like I said, like if you want more details about where things came from, what is VR, what is PR, interpolation, etc., check the previous videos. This is a super long question about the Otto cycle. If at the end of the day, what we found out was this is this. At the end of the day, what we found was, okay, the Q out, which was one of the things we were after, is 357.662, right? What else did we find? We found that T2, is 673 Kelvin. We also at some point found the pressure for P2 as well, and that was 1705 kilopascals. At some point we found T3 as well. That's one of the questions we needed to answer, and that ended up being T3 is 1539 Kelvin. We found P3 as well, and that ended up being 3,899 kilopascals. And then for 4, we ended up finding, didn't get much things for 4, right? Just got the VRs and the UR, so we didn't get really the final numbers here. For 4, we did get the temperature for T4, and that was 774 Kelvin. Okay, and this is useful to do. This is a useful exercise to actually go back and check the things that you found as you're solving this, right? Especially if you have time. Obviously, on an exam or midterm, that's not always possible, but in this case, it needs to check out, right? You can see, for instance, that the pressure 1 is the smallest one. Then we have pressure 4, then pressure 2, pressure 3. So if pressure 2 is not between pressure 3 and pressure 1, we have a problem. It's not the case. We're good here. What about temperature? Well, as we're compressing, you would expect the temperature to increase, and here we're giving energy, so we also expect the temperature to increase. So we're going from 300 to 600 to 1500, so it makes sense too. Okay, so these are the things you can check, after you've finished to ensure, it makes sense. And then finally, obviously, this temperature here needs to be greater than the initial one, yet smaller than T3. Okay, so it checks out. If you guys have any questions, as per usual, leave them down below in the comment section. If you want, a different explanation on this, you can check, like I said in the beginning, the previous video exactly on the same question, which goes into more details for some parts. And if this video was helpful, consider giving it a like. We'll talk soon.